Okay, we're going to look at section 2.9, dot products. Okay, let's say here's an example to kind of give us an idea of how we can use dot products. And let's say, for example, we're looking to find the angle, let's say, between these two cables at this common point. Okay. Another example we have is, let's say, and this is in a future chapter, a future topic we're going to be taking a look at, this idea of a moment or a torque. Really, what it means is essentially applying a force at some distance to act on some point or some line here, okay? In this case, what are we doing? We're applying a torque to either loosen or tighten this bolt, okay? So one of the things we might need to know is, like we have, if you wanted to create a vector, you could create a vector, let's say from, this point to where the hand actually meets, and another vector here. So we could say like here to here, maybe a vector from here to here. It really doesn't matter. It's just going to be in the opposite direction. But let's say we're finding, in this case, their example, we're saying, okay, what if we wanted to know the angle between these two, right? Between a vector made from this bar and a vector of the force, okay? So we can actually use a dot product to do that. Okay. Okay, so just by definition, what a dot product is, we can define it if we have two vectors and we're dotting those two together, finding the dot product of those two vectors. What it is going to be equal to just the scalar components of the vectors times the cosine of the angle between them. Okay, so with manipulation, you can actually go through and determine the angle, right? So if you divide it by the magnitudes multiplied together and then did the inverse cosine of each side, you could figure out what that angle is. Okay, just a couple of points here. What you'll recognize is when you do the dot product, you come up with a scalar on this side. Okay, so it's going to give you a scalar result. All right, so it's just the product of the units of the units A, B. Okay. Now, what's the other definition? So it's like, what do you get on the left-hand side? Okay. So the inner product or dot product is basically just you're going to take the terms like ax times bx, ay times by, az times bz here. Okay, so these are just the magnitude of those. And really, it's just because of this. If you do a dot product of two vectors, it comes out of two vectors that are mutually perpendicular. Then you're going to come up with 0. And really, one of the ways to think about a dot product is like projection of one vector on another. So if you had like I and j are basically 90 degrees off. So if you have one vector going straight up and one off at an angle of 90 degrees, you would find that essentially if you took and tried to get a projection of how much of this vector runs along like the horizontal direction, a vertical vector runs along a horizontal vector and they're off by 90 degrees, there'd be none of it would actually go in that direction. And if you did it, mathematically, you'd find that cosine of 90 would give you 0 essentially. So, it comes out mathematically and conceptually also. Okay, so the only time you're going to come up with a magnitude of 1 is when one vector essentially is parallel to the other, or in this case, they're running right on top of each other. Okay, so when you do the dot product, this is essentially what the left-hand side of the equation comes to be. All right. Okay. So, like I said, we can go and manipulate this equation. All right, the equation we had previously, as I talked about. First, you can find the if you're looking for the angle between the two vectors. Here's just the magnitudes. The x components multiplied together, the y components multiplied together, and the z components multiplied together. Okay, so that gives us the left-hand side of the equation, the numerical value. Okay, for that. And then you could just find the magnitudes of these two vectors, right? Using Pythagorean theorem, say, to do that. Okay. And then, like I said, you just manipulate that original equation, and it just comes out to be the inverse cosine of the dot product or inner product, which is just this, divided by the magnitude of A times the magnitude of B. Okay, and then the end result is the angle between these two vectors. And like I said, the way to think about it is that result is essentially like how much of like B is on A and how much of A is on B. It really doesn't matter. But that would be like if you drew a line straight down to here, that magnitude would be here, okay? Which you'd find that to be true when you did this. All right, but this overall, this is a way to come up with the angle between those two vectors. Okay. Okay. The next part of this is thinking about it in terms of a projection, like how much of one vector is projected on the other. Okay. And you can do that with, and it's really the same thing we did previously when we had two-dimensional vectors. And you can think about it like this. Let's say that you have this vector A, and this is kind of like, this could be our x. It doesn't have to be, but let's say this is our x axis and this is our y axis, which the whole point of it would be that, you know, for that example, but they both have to be 90 degrees off, right? This axis, these are mutually perpendicular axes or lines. So by doing this, this is essentially just our component. If we had a vector A, this is like our x component, right? That's all essentially this is. So we're saying how much of A is projected onto this other vector UA, okay, in this direction. All right, so this would give you this magnitude of this part of the vector. Okay, so this has a definition. It's essentially a scalar projection. One of the things that you need to find this unit vector. All right, or if you think about it, let's say this was the x-axis. If this was the x-axis, this would just come out to be I. All right, and this would be J. Okay, so but in general, you would just find the direction. And remember, this is just a direction vector. So UA is just along this line. So UA is the direction of this line, A. But what it tells us is that in general, we can solve it this way. Our very specific case is when this is X. When it's X, this just becomes I. Okay? Okay, so in the previous kind of example that I showed you, when we were talking about, in this case where I said it was I, for at least conceptually what's happening, the projection, what actually happens here is that you come up with the so-called parallel component vector, okay? So the parallel component essentially is when you're using, it's basically the or the x component of the vector if you're using, x and y axes, but just in general. And the general expression is the magnitude times its direction, okay? Like I said, if this was I, this would just be AX, right? This would be the vector AX in that direction, in the direction of X, okay? All right, so the next thing you can do, of course you can find the perpendicular component by doing this, just a squared minus the parallel component squared and then square root of that. And really the definition is this, if you think about it. The way you can think about it is, here's the way to think about it, is just A is just the parallel component plus the, the parallel component plus the perpendicular component, okay? So this is just like before, where we had X and Y axes, right? This would be my x. This would be like a of x vector, or ax scalar times I. And this would be, this component here would just be ay times j, right? And that would give us our vector. So you'd have your j and your x component. And that's your two-dimensional vector. So like all you do here is just rearrange it, right? You take this equation, you rearrange it, and then it gives you this magnitude. And like I said before, is what you have is, if you square both sides, you can say, the squared terms are times multiplied together. But what you recognize here is that essentially this is just rearranging to come up with the scalar, it's just rearranging our original equation, right? Because really it's just like a of x squared. So if you squared both sides, add this to this side over here, you'd have a parallel squared plus a perpendicular squared, and then did the square root of both sides, that would equal a. Okay, so it's just, this is just our standard distance formula rearranged. Okay, and you would see it just by using this equation. Okay, so taking a look at some examples. All right, so we have a force acting on a hook at a point A here, and we have the angle between the, so we need to find the angle between the force line and the magnitude of the projection of the force along the line. Okay, so we need to find out a few things. We have, well, we have two vectors, right? So this is a line between AO, so here's AO, and then our cable here. Okay, so those are our two vectors. So first thing we need to do is find this vector RAO, right? And when we do that, we already have the force vector. That's already given. All we need to do is apply the formula that we previously looked at to find that angle. Okay? And the next part of this is you want to find the projection. You just have to do the dot product between the two, right? And that's what we had talked about previously. So to get the magnitude, you just have to do the dot product between these two. Okay, between these two unit vectors. And if it makes any sense, if you look at it, you say, well, okay, this essentially is that vector, f, right? And dotting it between the two, if we take a look and go back here, just taking a step back a few slides, if we look back at how we defined this, we found the scalar projection. So you're dotting it with that unit vector in that direction, and then that's going to give you the actual magnitude of this. That's in this direction. Okay, so we're doing the same kind of thing as what was done here. Just going back to that example, go forward a little. Okay, so that's all essentially this is. It's finding that parallel component, or the component that's parallel to this AUAO. Okay, how much of this force is in the direction of this line, right? So just going through, and you can work through the actual math in these problems to solve it. And first thing is you come up with this, and of course, once you come up with the vector, right? All it is saying, you're here, going from here to here, in the x direction. So let's see, we were at position. Oh, here it is. So you're out 1 meter. So you're going from essentially in the x direction, you're going in by 1. That's why we get a minus. And then in the y direction, you're going positive y direction because you have a vector basically from here to here. And that's by +2. And then you're going down in the z direction, so that's why you get your minus 2k. All right? And then, of course, you can find, here's the magnitude, here's our vector, and here's the magnitude. F is given. All you have to do is find the magnitude of f. Okay? Then when you do the dot product, all you're doing is you're dotting, like here's the x components, the y components, and the z components multiplied together just from, these two equations here. This one and this one. Okay? And then all you have to do is apply that other equation. You've got the values now. Here's your 18 kN, 18, which is just the dot of these two, divided by the magnitude of the two, which you had already, which is 3, and 11.22, which you found. And continuing on. So let's see. Okay, so continuing on, we need to find this vector in the direction of AO. And the way you could do that, you'd recognize that it's in the direction of it's essentially this vector, RAO is equal to UAO, which is its direction, times this RAO. Okay, so we already found this and this, so all we do is just plug it in. Plug in these numbers for these values, or the equations into this, or the equations we already had into this equation. And this is what you're going to come up with. And then now you just do the dot product of this thing with our f, and here's the result. And here was another way to actually find that, because we did have an angle and we did have a magnitude. So this is a little bit quicker. Okay. All right, here's another problem. Okay, so continuing on, and this is really basically following, the same approach as before. We're going to try to find the components acting parallel and perpendicular. Well, it's pretty easy. We find the parallel component, and it's easy to find the perpendicular component from this, just from our standard equation. The parallel, or sorry, the perpendicular component just equal to the parallel minus. I'm sorry, the vector itself minus the perpendicular. The perpendicular component is just the vector itself minus its parallel component. Okay. All right. So in order for us to do that, it's just going to be, we need to find this f, a vector, right? We have a magnitude and we have some information in terms of its direction, so we need to use that. And then, of course, we need to find this vector here that represents our pole. And then we also need to find the unit vector, or the direction, okay, which these two are pretty straightforward, okay? Once we do that, now we can solve for our parallel component and then our perpendicular component, like I said previously. You have the squared, just from previously what we had talked about, you have the vector itself squared minus its parallel component squared, and the square root of that gives you that magnitude in that direction. Okay, that's perpendicular to the previous one we already found. Okay, so these are off by like 90 degrees. Okay, so like as previous, you just go through the process saying that from this point A going back or forward. So let's see, maybe a little tough to see which. Oh, okay. So here's our 4. Okay, so that's minus 4 because we're going. Let's see. Oh, sorry. This is O to. This is a vector O to A. As long as we're consistent, either A to O or O to A. In this case, we'll go from O to A, and the only difference it would be is like in the exact opposite direction. Okay, if we had the signs mixed up, but if we're consistent, you'll see it'll work out. Either you do ROA or RAO, you would still come up with the same thing because your unit vector would also be in the opposite direction. Okay, so you'd see it work. It would work out. Okay, so but we're going to do ROA. So from here to A, so it's minus 4 in the x direction, plus 4 in the y direction, and plus 2 over here. You can see it, and the k direction. Okay, so we follow the same process, and you find the magnitude. And then, like I say, you can use, so now you have the magnitude, you just divide, you take this one, the vector itself, divide it by its magnitude, and then you come up with the direction, okay? Now, the second part of this is how we actually go through and define this vector f, right? What we really have is like an intermediate vector that we have to think about, like, this is what we had done previously, was that we have like a vector here. Now you can do this in 2 steps where you come up with like an intermediate vector here, and you just you're basically coming up and saying that this vector relative to this vector here. You're kind of making a 2-dimensional problem with the 60-degree angle. You could do it 2 steps if that's easier to come up with this like f prime, if you want to call it. But all it is essentially saying that we're taking this vector and breaking it up into the z component, which is this, and its component here, okay? And when we do that, what happens is essentially you're just going to have the magnitude of this times the angle between them, okay? And this gives us, this is the same here, this is the magnitude essentially of this vector here, okay? Then we're using that in a 2-dimensional space, which is represented by this plane. Okay, so it's like we first come up with an answer for the magnitude of this, thinking about like this, what is it, light blue or whatever, plane with these two. Okay, so we're taking how much, 600 pounds, the much that's projected along this line essentially. And that comes up to be 600 times cosine of 60 degrees, okay? So that's like this vector's magnitude, all right? Then we use that in 2 places, here and here, because we're taking this vector and we're breaking it up into its, essentially its y. I'm sorry, this is the y one. And this is the the x one is this, okay? Because it's opposite the angle. The opposite the angle one is the x component this time. That's why it's the sine, and the other one is the cosine, which is the adjacent side here, okay? And of course, when you originally solved the problem, one of the dimensions already was z, so we just use that directly. So we're saying opposite of this angle is this side, and that's how this comes out, okay? So now we just solve for this, and we come up with our three components here, okay? The next thing to do is just do the dot product, which is essentially what we did previously. And when you do it out, here's the dot, here's the UAO. So it's just 150 times this minus 2/3. 259.8 times 2/3 and 1/3 times this. And when you go through and solve that, the magnitude comes up to be 446 pounds, okay? And we continue on. Oh, sorry. Then we just use that. Well, we already had F2, right? Which is just this magnitude of this minus the parallel component squared. And then we just solve for this, and there it gives us 401 pounds, okay? All right. Which is just basically the amount of the force that's perpendicular to this line. While this one was the parallel component, parallel to this line. All right, continuing on. So we continue on, and we have the 300-pound force acting off in a direction. And we are given some angles here. Same thing. It's a little bit, maybe a little tougher to see this one. But we have the same process. Okay, so we're looking for the magnitude of the projected component along this force, acting along the line O to A. So from this to here. Okay, how much of this force is acting along a line from this point to this point? So we follow the same basic process here. We're going to look for an angle between the two. But first thing we need to do is we come up with a vector ROA. Then it's unit vector as before. And we don't necessarily have to come up with the, well, we still have to work through the F component, the F vector, and figure out like what its components are. But that's also part of this, right? So then we find the angle between them. And then when we find the angle between them, we can actually find the magnitude of that projection along that line just by doing the dot product between the two, okay? And here we go. So ROA, and then its magnitude is no problem, just thinking about like its direction. So from O to A, it's back along the x-axis by this 450. Okay, so like this one's 450. Well, you have your 300 plus, if you think about like we have our vector here, or the length of the vector from, or length of the line from the point from here to here is 300. And then we're given the angle. Might be hard to see that, but it's really the angle between these two along the plane made by Z and X. So we can actually come up with the length from here to here, which is essentially just the 300 times the sine of 30, because it's the opposite of the angle here, side opposite the angle. So that's where you get your 450. And then the other one is the, in this case, the J component, which is how far up. Oh, sorry, not how far up. It's over to the off to the right. That's the 300. Okay. Then this one is this component right here, essentially. Okay, from this point to here, and that's just going to be 0.866, because it's going to be the cosine of 30 degrees times this. Okay, so you got 0.260. So easily we can find the magnitude. It's 0.60, and then use those, a piece of information that we already have. We have the vector divided by its magnitude, and we come up with a vector for the unit vector. Okay, one of the things about this, unit vectors always have magnitude of 0. I'm sorry, magnitude of 1. Okay, so if you did square root of this, each squared each term, magnitude would come out to be 1. All right, so continuing on. The next thing we can do is come up with the magnitude of this vector, right? If you notice, we have this, we have a plane. We've got something defined here. We have an angle 30 degrees between, so way we can think about this one is like for this f prime is we have, think about this as a plane, right? This is the plane between, this and made by the y component in this, okay? Or maybe a better way to think about it is, f prime, we have, if we look at it from this perspective and we just want to find the magnitude here, and then once we have that magnitude, we can break it up into its components along this surface, okay? And then break it up into its x and y. Okay, so just looking at this and thinking about it, we can refer to the equation, what the different parts are. So what we could do is we think about this vector essentially is going to be in this plane, the zx plane. Okay, so it's going to have two components, and we can break it up into x and z components, and that's essentially all we're doing here. So we're taking the magnitude of this thing. Okay, so we have like, here's my 300 newtons, and we're breaking it up into two components. Essentially, we think about a plane here made by this angle and this vector, which actually this vector is going to go right along the x z plane. Okay, but we find that magnitude, which is essentially just going to be the the sine of this angle, because it's essentially this side right here times 300. Okay, so when you do that, you come up with your 150 newtons. All right, so now you have this. Here's our force vector. Here's the magnitude of that force vector, and we want to take and find out how much of this force vector, is going like off in the x direction, and how much of this force vector is going in the z direction. Okay, so we're doing like these two first. Well, the first one is that if we just take a look at it, what we recognize from this f prime's perspective, the z component, because this is right along the x-axis, parallel to the x axis, at least in that plane, right? So the z component is just going to be like you have an angle between these two vectors. The z component would be essentially straight up. If you drew this straight down, you would find that really it's this right here, right? That angle, that's the 30 degrees. So you break it up into its x and its z components first, okay? How much is going in the x direction and how much is going in the z direction, because this is right along that plane of the x and z. So here's your x component, and here is your, and it's got the negative direction in the x direction. It's going off in the back, and then it's going up. So here's my z component, okay? So the next part of this is we want to figure out like how much is in this direction here, okay, which is in the y direction. Well, here's my vector, and what you recognize here is that this is essentially just the cosine, right, of this vector, because this is the value we're given, the 30 degrees between these two. Okay, so whatever it is, we make a plane here like we previously did, so a plane between this vector and my y-axis, and when we do that, it's just essentially going to be this value times the cosine of this angle. Okay, and that's where this one comes from. So now we have the three components of our force vector F. This one's a little tougher, I think, to look at and visualize. When I looked at it first, it's like, oh, what's this actually? Oh, okay, this is a plane here. And then we create this other vector that's right along the x, right along the plane made by the x and z-axis, and then it's easier to break it up that way. So here we have our components, then we have our magnitude. Okay. Continuing on, then we just do the dot product. Previously, the f vector dotted with ROA, which we had previously. Here are all the components. Well, we go and solve it, and then we can use that, and then use the multiplication of these two. Almost looks like a cross product here. But this is the multiplication sign in this case. It's just multiplying these two together. Cross product is something we'll look at in the future. But we use the same symbol, but it'd be vectors. So then here's our magnitude divided by this magnitude, and then we have just the inverse cosine to come up with that. Okay. Then the last part is, now that we have that angle, we can go ahead and find the magnitude just by doing the dot product. All right. And the alternative approach is just this. We have the angle between the two. So we can find it this way too. Okay. So that's about it. That's it for chapter 2. And the last one was the dot product, which is, using it to find a projection of, one vector along another line or determine the angle between those two vectors.